let's talk about this equation. So once again, I have cooked up a delightful little monster for you guys to enjoy. That's right, another creation from the evil math laboratory. Just look at this thing. Product notation, summation, integration. I even used a derivative, which I seldom do. And of course you can pause this video at any time and try to solve it on your own. Okay, so let's dig in. Now, while this equation looks like it might belong in some advanced physics book, it actually is a bit of a red herring. Your first clue is this derivative, which is inside of the integral, especially when both of them are trying to operate with this x here. Yeah, that doesn't normally happen. Those two kinda cancel each other out, but they do look cool together. Now, before we dismiss them, let's first figure out the rest of this jazz. A good place to start is this natural log over here. So we have this x right here, which we can pull out like so. This, of course, leaves us with this. Ah yes, a dumb, redundant way of writing the number 1. So this just leaves us with this product notation. I like using these guys a lot because they look intimidating, but you can probably already guess that this is all a bunch of hot air. You can just kind of blow this thing away and take this 2 and put it over here. I just love creating these redundant equations that have no real purpose. Speaking of which, now we have this square root over x squared. This is one of those things that looks like it might cancel out, but we have to be careful. This actually gets rid of any negative values of x. For example, say x would be -2. That would force it to become just a regular +2, which is why I implemented this confederate over here, which gives us the sign of x. So imagine that x is -5. This reduces the -5 into a regular 5, and this becomes just -1, giving us back the original -5 we started with. Or we could just cancel those two things out, because after all, they are the same thing anyways. Which leaves us with this thing. Ah yes, one of my favorite redundant summations. This creature was my original gateway drug into calculus. So the way this works, imagine that x is a certain distance. Our first bottom term, 2 to the power of 1, will just be 2, which divides our distance by half. We then add the second term, 2 to the power of 2, which gives us a quarter. 2 to the power of 3 gives us an 8. 2 to the power of 4 gives us a 16th. And we can just keep doing this indefinitely. We are basically cutting in half the remaining length and adding those segments in a kind of perpetual shrinking distance. The idea is that if you could do that an infinite amount of times, you would end up with the original value of x. This idea fascinated me, and I spent a lot of time thinking about it. It would pave the way to my understanding of limits, and an eventual interest in calculus and other higher maths. For our situation, however, all it means is that we can get rid of this thing, leaving us with, once again, just the x. And here we are back to this integral derivative business. Scary looking symbols that become nothing more than just dust in the wind as they annihilate one another. So there you go, an impressive looking collaboration of self-canceling terms that reduce back into our ordinary x. Basically a bunch of fluff and puff just to conceal our variable. Now what I find neat about this equation is that we can use the integral to make our x into some particular value. To do this, we have to make our indefinite integral into a definite integral. And we do this by plugging some limits into it. By making the bottom into a and top into b, we change our x into b minus a. This means that we can use a simple subtraction to implant whatever number we desire. For example, if we use 3 as the top and 8 as the bottom, we end up with -5. I think this is pretty neat. Definitely one of those fun equations you can sneak onto a blackboard before the class begins. I hope you liked this one, and I hope to see you all in the next one. Like, subscribe, and as always, thanks for watching.